Hello, everyone, to the live session where we're going to solve this specific past paper, which is 5070, paper 4, made in 2009. It's a 5070, your O levels, GCE O levels ATP paper. If you're doing IGCSE, then even then it's going to be very helpful because uh, a lot of the experimental concepts are pretty much the same. So you can also join in. It's a 1 hour paper. You have your instructions. They're written in front of you. Uh, Now we're going to start this paper, and we're going to start with the first part, which is uh, which says that a student did the following experiment to find the formula of magnesium oxide. So there's an experiment that's happening, and magnesium oxide. The main goal of the whole question is to figure out the formula of magnesium oxide, which we pretty much already know. So I'm just going to write this down because Mg is group 2, so it's always 2 plus. O is group 6, so it's 2 minus. So it has to be, at all costs, it has to be MgO. There's going to be one Mg and one oxygen, but we have to do this experimentally. So we're going to ignore that for a second. The first part is a 10 centimeter length of magnesium ribbon was loosely coiled and placed in a previously weighed crucible, which was then reweighed. So you're adding magnesium to a crucible and you're being asked to find or calculate the mass of magnesium. The mass of magnesium can be found out by subtracting the two values. You're going to subtract these two values. And if you do that, if you do the subtraction, it's going to be 13.08 minus 12.72. Make sure to write your working every time just to be on the safe side. Sometimes what happens is that you get the value wrong. So your working is going to help you in your marks if you're able to show the working. You might make mistakes on your calculator, so always remember to show your working. So it's going to be 13.08 minus 12.72. Let me quickly do this on my calculator, and this comes out to be it's 13.08 minus 12.72, and the value that I get is I'm getting 0.36 grams. So I'm going to write that down, 0.36 grams. The next part is the crucible was placed on a pipe clay triangle and heated strongly for several minutes. During the heating, the crucible lid was lifted and replaced several times. The magnesium was converted into magnesium oxide. So a reaction is happening where magnesium ribbon is being added, is being heated, and it's reacting with oxygen gas. So that's the only thing it's going to react with. So the reaction that would happen is it's going to be Mg reacting with oxygen to produce magnesium oxide. Now the question B part 1 is why was it necessary for a lid to be placed on the crucible during the heating? Now the lid is placed on the crucible is that when you're heating strongly, some substances, there might be some water trapped, which might change into steam, and some of the substances might fall out of the crucible. So to prevent any substance from falling out of the crucible, that's why a lid is placed on top, because whenever you're strongly heating, substances they hiss and they spit, which basically means that if there's any water trapped, steam would form and the substances would explode. You might have noticed that if you heat a substance strongly, it generally the bubbles produced, gases are produced, which tend to spit, which means they explode. Tiny explosions happen, very tiny, and the substance might fall out. So why was it necessary for lead to be placed on the crucible during heating? So substances don't fall out. Then the next part is why was the lid lifted during heating? That's because you wanted to react with oxygen, with air. So oxygen has to enter, and which is why the lid is lifted during heating. So to allow oxygen gas oxygen gas to enter. The next part is describe the appearance of magnesium. Magnesium, it's like any other metal. It's a grayish, shiny, metallic substance. And the appearance of magnesium oxide is MgO. Remember, metals, transition metals have colored compounds. But if a metal is not a transition metal, it's not going to be a colored compound. It's going to be white in color. So this is going to be white solid. It's a group 2 metal. Group 2 metals are white in color. The next part of the question, let's move to the next page. Now, in this part, after cooling, the crucible was weighed. It was then reheated, cooled, and reweighed. And the final mass of the crucible plus magnesium oxide was found, and it came out to be 13.32 grams. Why was the crucible reheated? Now, the purpose of reheating a crucible is that what were you trying to do? If you go back and have a look, you were basically trying to heat this magnesium and react it with oxygen. So the purpose of reheating it over and over again is to ensure that all the magnesium has reacted with oxygen. Uh, and whenever Mg reacts with oxygen over here, the mass would increase. Mg oxygen will get added and MgO would be formed, which is why you always reweigh it. So if the mass is constantly changing, that means the reaction is still going on. Mg, more oxygen gets added, the mass increases. There's still some unreacted Mg, oxygen gets added to it, MgO forms and mass increases. Once you've run out of all of Mg, all of the Mg has reacted, uh, then even if you reheat it and reweigh it, uh, oxygen is not going to get added because all the Mg has already reacted. So the mass stays constant. So the purpose of why was the crucible reheated? To ensure that of the magnesium, all of the magnesium has reacted. And you're being asked to calculate the mass of magnesium oxide. Now this over here is, if I underline this over here is the mass of magnesium oxide plus the crucible. So I need to get rid of the crucible from this mass. Go back and have a look. The mass of the crucible is already provided. It's 12.72 grams. So what I'm going to do is I'm going to go back and I'm going to subtract, show you working again. I'm going to subtract, I'm going to take 13.32 grams and I'm going to subtract the mass of crucible, which was 12.72 grams. And the answer that I'm going to get on my calculator, it's going to be 0.60 grams. The next part is we're being asked to calculate the mass of oxygen that reacted with magnesium. Now we found two things. One is that we found the mass of magnesium oxide, which is coming out to be 0.60 grams. The other thing that we already found previously was the mass of magnesium, which came out to be 0.36 grams. Now we heated this magnesium, which is 0.36 grams. Don't forget to write the unit. And oxygen got added, it reacted with it, and it ended up forming MgO. Remember, we don't know the formula. I'm just using this to explain. Remember, right now we don't know the formula because that's the formula we need to actually calculate. So don't actually write this in your answers. Uh, Now MgO came out to be 0.60 grams. So what is the thing that got added? It was oxygen. So I'm going to subtract the two values. It's going to be 0.60 minus 0.36 grams, and this comes out to be 0.24 grams. And now in the last part, you're being asked to calculate the formula of magnesium oxide. So we're going to try and do that. The mass of magnesium is already known. The mass of oxygen is also known. This came out to be 0.24 grams. This came out to be 0.36 grams. These have been calculated previously. So how do you calculate the empirical formula? There are two steps to it. The first step is you find the moles. You divide by the AR. So I'm going to divide that by 16. I'm going to divide this by the AR of magnesium is 24. So you're going to do that. So it's going to be 0.36 divided by 24. So both values, they actually come out to be 0.015 moles. And The last step is you find the simplest ratio. Now, this is the mole ratio, but it's in decimals. What's the simplest whole number ratio? For that, you divide by the smallest, which in this case is the same value. It's 0.015 divided by 0.015. And I'm going to divide this by 0.015 as well. And the value that I'm going to get is the ratio that I'm going to get is 1:1. So that means in the formula, Mg is 1 and oxygen is also, it's also coming out to be 1. The next part is that question number 2. A student electrolyzed molten lead to bromide and dilute sulfuric acid in the apparatus shown below. So there's an electrolysis that's happening, and it's lead to bromide and sulfuric acid. Both of them are getting electrolyzed. This is your cathode, the negative side, and the positive side is your anode. And you have your electrodes on both sides. Now, you're being simply asked what was produced at the electrodes A, B, C, and D. So we need to figure out what the products are going to be. So I'm going to start off with A and B. It's molten lead to bromide. So molten lead to bromide is consisting of two ions. One is lead 2 plus. So there's Pb2 plus, and the other one is bromide. Bromine is in group 7, so it's Br minus 1. Now the negative cathode is going to attract the Pb2 plus ion, and the positive anode is going to attract the Br minus 1 ion. Positive attracts negative ions. Negative electrode attracts the positive ion. Uh, so there are electrons that are coming in. Remember, at the cathode, reduction happens. The battery is sending these electrons, and these electrons are going to be gained by Pb2 plus. So over here, you're going to have Pb2 plus. That would end up gaining two electrons. It needs two electrons to form lead. So at B, the battery is sending electrons. At cathode, reduction happens. The ions, whichever ions they approach the cathode, they're going to gain electrons, and they end up gaining electrons to form lead. On the other side, on the positive side, anode side, Br minus 1, it ends up losing electrons. So electrons are lost. The battery takes away electrons or removes electrons. The positive side of the terminal of the battery, it attracts those electrons, and those electrons are lost. Br minus 1 ends up losing electrons. And the equation at this side would be that Br minus 1 would be losing electrons, but it's it's a diatomic molecule. Remember, group 17 is all diatomic, group 7 is all diatomic. So I'm going to double it. So it's going to lose two electrons to form a Br2 molecule. Two bromine atoms are going to be produced, and they would end up forming, because they exist in diatomic state, so they would end up forming a molecule of Br2. So option A is Br2, and option uh, B is, if we identify B, that's lead. On the other side, this side is dilute sulfuric acid. So that basically means that dilute means there's water present. Now, sulfuric acid has two ions. One is H plus 1. So the H plus 1 ion is attracted to the negative cathode. And the other side is SO4 minus 2. That is going to be attracted to the positive anode. So negative ion gets attracted to positive, positive ion gets attracted to the negative side. Uh, your solution is going to have two ions. One is H plus 1, and the other one is OH minus 1. So you have two more ions coming in. One is H plus 1, and the other one is OH minus 1. These ions are always present when there is water that's present. These two ions come from water. So who's going to gain electrons at the cathode? The battery is sending in electrons. Reduction is going to happen. Someone out of these two, I mean, these two are the same thing. So they're going to end up gaining electrons, and it's going to be H plus 1. And the problem is that H plus 1 is also diatomic. So it has to be, you have to double that. 2H plus 1 would gain two electrons to form an H2 gas molecule. And on the other side, you have two options. One is OH minus 1, the other one is SO4 minus 2. So who's going to end up, who will be the one who's going to lose electrons? So battery is taking away electrons, the positive side is pulling electrons. So one out of the two has a higher tendency to lose electrons. So how do you figure out which one has the higher tendency to lose electrons? So there's this series at anode that has to be remembered, and that is this one. Now in this series, the one that's lower in this series, they are the ones that have a higher tendency to lose electrons, which in this case, if you compare SO4 minus 2 with OH minus 1, then OH minus 1 has a much higher tendency to lose electrons. So you're going to select OH minus 1 at the anode. And the equation for OH minus 1 has to be remembered as well, because OH minus 1, when it loses electrons, it decomposes. Ends up losing 4 electrons, ends up forming a water molecule and an oxygen molecule, and it decomposes. So this reaction has to be remembered as well. So at D, what's happening is hydrogen gas is produced. So I'm going to write that down. And at C, oxygen gas is going to be, it's going to be produced. The next part of the question is, what if anything happened to the brightness of the lamp when the following changes were made to the experiment? The first one is water is added to the dilute sulfuric acid. So they're basically making it more dilute. So if you're going to add more water to it, the ions would be less concentrated. And remember, how are the charges flowing? The battery is sending in charges. Electrons are gained by H plus 1 on one side and lost by OH minus 1 on the other side. So if there are fewer ions in the solution, if the solution is more dilute, there are fewer ions. So the electron flow would not happen very quickly because there are going to be fewer ions if you add more water to it. So the bulb is going to be dimmer because less electrons would be flowing. So remember, if there's more concentration of ions over here, the electrons would be gained on one side more easily because there would be more ions that would be sitting over here. For example, if you had even more H plus 1 ions, if the solution was very, very concentrated and there were lots of H plus 1 ions, then the electrons would be gained very, very easily. And but since you're adding water, you're making it dilute. That means the electrolysis or the flow of charges would not happen very easily because there are fewer charge carrying ions. So water was added to dilute sulfuric acid. Lamp will be dimmer. So there are going to be fewer ions present to carry charge. Then the next part is the heating was stopped and the apparatus was left to cool. Explain your answer. So you're stopping heating. Now, they were only heating on this side, not that side. That was aqueous, so the ions were freely moving around. Remember, for electron flow to occur, the ions must be mobile. I mean, this lead 2 plus has to come to cathode to catch this electron. This electron is coming in, it has to grab that electron, so it has to be there. If this lead 2 plus ion is stuck over here, if it's in solid state, it won't be able to move over here and carry this or attract this electron. Uh, so the ions need to move uh, to catch these electrons. The Br minus 1 have to reach this anode A, where they're going to be losing electrons or producing electrons. So the ions cannot move. So in solid state, if lead 2 bromide becomes solidified, no electricity is possible. So the heating was stopped and the apparatus was left to cool. Bulb will not light or will be dimmer or simply it won't light. So the bulb will not light. as ions will not be able to move freely. As ions will not be able to move freely. The next part is it's MCQs. A student recorded the results of four experiments with ethanol. Which result was not correct? The first one is on reaction with potassium dichromate 6, the color of the solution changes from orange to green. So this is a typical reaction of an alcohol, and it's a correct reaction. What happens is this reaction is known as oxidation of alcohols. So you have ethanol, which is eth means two carbon atoms, and all means there's going to be an OH. This carbon is going to have two hydrogens, so I'm going to draw these two hydrogens, and this carbon is going to have three hydrogens. Oxidation is going to happen, which means that when oxidation happens, what that basically means is that the OH carbon, it changes into a carboxylic acid molecule. The rest of the molecule remains the same. The only change that happens is to this carbon atom over here, which is an alcohol initially, but now it has changed into carboxylic acid. The reason why it's called oxidation is because oxygens are getting added. Now, how does oxidation happen? Because of this oxidizing agent, which is K2Cr2O7 acidified, and you use reflux. And the color change that happens is orange to green. Remember, K2Cr27, the color change is always orange to green. So this reaction is correct. Remember, they were asking for which one is not correct. Ethanol dissolves in water. That's a fact. All alcohols are very soluble. So that's a fact. Uh, on combustion, a gas is produced that popped in a flame. Now, any gas that pops in a flame, that's the test for hydrogen gas. So combustion is never going to this is basically the correct answer. This is not going to happen because when you combust something, specifically an alcohol molecule, for example, C2H5OH, or most organic molecules, what are going to be produced is a carbon dioxide molecule is going to be produced, and water is also going to be produced in the reaction. So two carbon dioxide molecules, and you can balance this three water molecules and three oxygen molecules on this side. So ethanol, when it burns, it produces carbon dioxide and water, not hydrogen. Actually, so hydrogen is never produced in combustion. The last one is also correct. Ethanoic acid and ethanol are going to produce this ester. So we can quickly draw this ethanol and ethanoic acid. How are esters formed? Draw an ethanol molecule. So it's two carbon atoms and an OH, and carbon is supposed to make four bonds. So add in all the hydrogens so that each of the carbon atoms is making four bonds. Reacted with ethanoic acid. Ethanoic acid is a carboxylic acid, so it's supposed to have double bond O and OH. And this carbon over here has three hydrogens. The next part is the OH is going to be removed and the H is going to be removed, and a condensation reaction would happen. And the two parts are going to link up and they're going to join in the middle. And that's going to be your ester link. So this over here is your ester link. That's known as an ester link, and an ester is formed. And the name of the ester is because around the ester link, this side has two carbon atoms, so that's eth. That's how you name them. This side also has two carbon atoms, so that's also eth. The single O side is called YL, and the double bond O side is known as O8. So that's ethyl ethanoate, and that's the ester that's going to be produced in this reaction. So that's a true statement. Let's move to the next part. The apparatus in the diagram was used to compare the rate of diffusion of a gas with the rate of diffusion of air. Uh, so you're comparing the rate of diffusion of air. The first thing is air is what is air? That's what we need to figure out. It's 78% nitrogen and it's 21% oxygen. The rest of the 1% is We can ignore the rest of the 1% for now. Now, nitrogen is has a mass or MR of 28. Oxygen has a mass or MR of 32. If you calculate the average mass of air or AR of air, that comes out to be actually 29. So remember this: whenever somebody is talking about air, its average MR is 29. So that's the average MR of air. It's 29. The after shown in the diagram was used to compare the rate of diffusion of a gas with the rate of diffusion of air. So air is inside. So I know the mass of air. The mass of air is 29. Uh, why am I basically trying to measure the mass of air? Because the mass determines the rate of diffusion. Heavier gases, slower diffusion. Heavier gases don't diffuse very fast; they travel slowly. So heavier gases, slower diffusion is going to take place. Vice versa, if it's a lighter gas, then the diffusion would be faster. Now the question is, a beaker containing the gas was placed over the porous pop. For which of the following gases did bubbles emerge at Y? So the question is that in the experiment, bubbles are emerging at Y. What that basically means is that there's more gas coming into this porous pot. Remember what's going to happen. What's going to happen is you're going to have a bunch of unknown gas particles over here outside the porous pot. So let's say these green gas particles are the ones that are outside the porous pot, and there's air particles inside the porous pot. Let's ignore 29 for a second. So in blue, you have these air particles that are inside. Now the particles that are inside are going to diffuse outside. They're going to travel outside. They're going to randomly move and they're going to escape this porous pot. The porous pot means that it has tiny holes and the gas particles can escape. So the blue particles will try to escape. And vice versa, the green particles are also randomly moving around, so they would try to enter the porous pot. So the green particles would try to enter the porous pot. Now what's going to happen is that the green particles are going to enter the porous pot at a much faster rate. So for example, in 1 second, five of the green particles they move into the porous pot. So that's how many have I added? That's one, two, three, four, and let's say five. And the air, the blue particles are traveling much slowly. So let's assume that only two particles they actually randomly move out of the porous pot. Next second, five more green particles enter the porous pot because they're diffusing much faster. Same second, two particles travel out of the porous pot. But the end result would be because the particles are diffusing into the porous pot at a much faster rate. So there's more and more gas that's accumulating in the porous pot, and there's more gas that's accumulating in the porous pot. The gas particles would start pushing downwards. They need an escape because the gas is entering the porous pot at a much faster rate. So these particles they travel through this tube, and bubbles would start to appear over here. So for this to happen, you want the green gas particles to travel, this unknown gas particles to travel much faster. They have to be lighter. They have to be lighter. They have to diffuse into the porous pot at a much faster rate. And they have to be lighter than air. Air is 29. So you want them to be lighter than air so that air moves slowly outside. Whereas the green particles, they travel much quickly inside so that there's more gas inside and the gas particles basically get pushed on the other side and you have gas bubbles over here. Now the only gas that's if you look at the options, the clear option is hydrogen gas. If that gas is hydrogen gas, it has a very tiny MR of 2, so the reaction is going to happen very quickly. Now let's move to the next part of the question, which is the diagram shows a chromatogram which was prepared using spots of 5 different inks. So there's a chromatogram happening. The ink spots are probably over here. They've been put over here, placed over here. And this side has been dipped into the solvent. And the solvent has started flowing upwards. And the dyes, if they're very soluble, they're going to flow with the solvent. If they're not soluble, they're going to stay behind. For example, this dye over here stays behind. Though this dye over here, it flows with the solvent. This is the solvent flow. So if a dye is very soluble, it's going to flow. If it's not soluble, it's going to stay behind. Now, in chromatography, what happens is that the distance traveled by the dye indicates uh, the identity of the dye. So if dyes travel the same distance, for example, these dyes over here, they are traveling the same distance. So I'm going to connect them with a line. So look at these dyes, they're all traveling the same distance. That indicates that these dyes are basically the same dye because they have exactly the same solubility and they travel exactly the same distance. Similarly, these dyes over here, they're traveling exactly the same distance, which means they must be the same dye as well. Same is true for these dyes, and the same is also true for these dyes over here. So dyes that travel the same distance pretty much indicates that they are exactly the same dye. So this is one dye, this is another dye, this is another dye, and then you have this, which is another dye. So in total, you have four different dyes. Next part of the question, question number 6, is some metals react with dilute hydrochloric acid to give hydrogen. Which of the following metals will not react with hydrochloric acid? So some metals are extremely reactive, some metals are extremely unreactive. So if you remember your reactivity series, it starts with K, Na, Mg, and so on. The metals that are below hydrogen in the reactivity series, for example, copper, mercury, silver, gold, and platinum. You can remember there are lots of metals that are above hydrogen in the reactivity series. So the ones that are below hydrogen in the reactivity series, they pretty much don't have a reaction with, at least with dilute acids. They need really concentrated acids. Uh, so not with dilute acids. So copper is the one that's really low in the reactivity series, which is why you make uh, your wires from copper, because you know that if you build a house and it has copper wires, you know that after 30 or 50 years or even 100 years, the copper, nothing would happen to the copper wires because copper is extremely unreactive. So unreactive metals have their own uses. Let's move to this question now. Acidified potassium dichromate 6 was used to oxidize ethanol to ethanoic acid. So this is the oxidation reaction that I probably talked a bit earlier. This is, you can have a look over here. This is the oxidation reaction that we talked about. You had an ethanol molecule, and it was getting oxidized to ethanoic acid. So the carbon over here got oxidized to carboxylic acid. Now, coming back to the question, what is the purpose of the condenser on top? Now, this apparatus is known as a reflux. Let's write that down as well. It's a very important apparatus. It's known as a reflux. Now, what you have over here, you have ethanol, which is an alcohol. Now, this is your hand sanitizers, etc. They all contain ethanol. Now, it's a very volatile substance. Volatile means it has a very low, not a very low, but it has a low melting and boiling point, and it evaporates easily. The problem with substances that evaporate easily is, and if you're trying to react, now your purpose was that you wanted it to react with potassium dichromate 6. But you can't react it with potassium dichromate 6 if ethanol immediately evaporates, and if the top is not covered, it's going to escape into the atmosphere. So no reaction would happen because all the ethanol, as soon as you put it in here, it's not going to react with potassium dichromate 6. It's going to gain energy and the molecules are going to evaporate. But if you put a condenser on top, the condenser is not going to allow it to evaporate. If you put a condenser on top, the condenser, what would the condenser do? that the particles, let's say these red particles are ethanol molecules that are trying to evaporate, that are trying to escape potassium dichromate 6. They don't want to react with it. So if these particles are trying to escape, the condenser cools them down. And if it cools them down, the particles would eventually fall back into the container and they would have to react with potassium dichromate 6. So they don't have any escape. Particles evaporate, they come back in, and when they fall into the container, potassium dichromate 6 is standing there and it's going to react with the alcohol. So the reaction is going to happen, and in this way, a volatile substance is able to react. You can't really close the lid or seal it because these are glass apparatuses, and these glass apparatuses they tend to explode because gases they build pressure and they tend to explode if you seal them tight. So you don't want to do that. These apparatuses are not very strong, so which is why the condenser is a much better option. Now we're going to move to this question, which is probably a moles question. And in this question, a student was given a bottle containing small pieces of scrap iron. So there is scrap iron that's present, and that iron needs to be now that iron is impure.